Okay, so let us continue with our discussion of basic open sets for the zariski topology. So let me again recall, you start with a polynomial g in n variables, and you look at the complement of the 0 locus of g and call it Tg. It is called the basic open set defined by g, and any open set can be written as a finite union of such basic open sets. And then we define the ring of functions on this basic open set to be functions of this form, namely these are the polynomial functions multiplied by inverting powers of g, okay, which makes sense because g does not vanish on that locus, okay. But then the fact is that this basic open set dg is actually itself isomorphic to an affine variety, and I've not defined what an isomorphism of affine varieties is, but I'm trying, at least I'll try to give you the isomorphism at least at the level of topological spaces, and this is how we do it. We take an the affine n space over k with the usual zariski topology and look at the 0 locus of g. This is a hypersurface, okay. If of course if g is irreducible, it is a hypersurface. If g is not irreducible, then it is a union of hypersurfaces, okay, and it will be a union of hypersurfaces which will be the reducible components. There will be hypersurfaces corresponding to the irreducible components of g which occur in the factorization of g, okay, and then the complement of this hypersurface is the affine open set, is the basic open set dg, okay. And this dg can be thought of as a closed subset, as a closed subvariety of an irreducible closed subset of a larger affine space, namely an affine space of dimension 1 more, and that is done in the following way. You look at the 0 set of gy minus 1 where y is the extra variable that you add to get the ring of functions on this affine space of 1 dimension more, and since this polynomial gy minus 1 is reducible, the ideal generated by gy minus 1 is prime, and the 0 set, therefore the 0 locus of that polynomial gy minus 1 is a hypersurface, okay, and it is a closed subset of this n plus 1 dimensional affine space, and it's an irreducible closed subset, and its ring of functions is defined to be the ring of polynomials on the ambient affine space divided by the ideal of functions that vanish on that hypersurface, which is just the ideal generated by gy minus 1. And the fact is that we have a bijective map from this basic open set here in an and this reducible closed subset, this hypersurface in an plus 1. So what is happening is that a basic open set in affine n space is being identified with a hypersurface in affine n plus 1 space, okay. So it may look at first it may look a little confusing because here it is open and there it is closed, okay, but you must remember that the affine spaces are of different dimensions, and you must also remember that the ambient affine spaces are of different dimensions, but the dimensions of these two spaces of course they match, okay. See, the dimension of a hypersurface is always always one less than the dimension of the affine space. So here it's n plus 1 dimensional affine space and its dimension is 1 less, so it's dimension n, okay. And this is something that I have not told you about, but this is something that I will try to explain to you. The dimension of an open set and a non-empty open set is essentially the same as the dimension of I mean it can be the dimension of a non-empty open set can be defined as the topological dimension, okay, and the fact is that the dimension of this will also the dimension of this will also be n, okay, and that coincides with the dimension of this. In fact, what will happen is that you know, dimension can be defined for any topological space, okay. It is defined to be the maximal length of you know, a chain of irreducible closed subsets properly contained in one another, each one properly contained in the next, and provided you start with indexing with 0 and then you take the length of the maximal such chain, okay. Essentially you should take the length of the maximal such chain and take away 1 from that, okay. So you can define the dimension of a topological space. In that sense you can define the dimension of any subset of any topological space, and it will turn out that the dimension of a subset is the same as the dimension of the closure of that subset. By going to the closure the dimension is not going to change, okay, and therefore you know, if you believe that statement, the dimension of d of g will be the same as the dimension of the closure of d of g, but then the closure of d of g will be the whole affine space, because d of g is a non-empty open subset of the affine space, and you know any non-empty open subset is irreducible and dense. In particular it's dense, so its closure will be the whole affine space, and by going to the closure you don't change the dimension, therefore the dimension of this is the same as the dimension of the affine space, and the dimension of the affine space is n, okay. So this is n dimensional, this is also n dimensional, so dimensions match, okay. And I told you it's a matter of exercise, it's a good exercise for you to check that this map is actually a homeomorphism. In fact, as I was trying to point out in the last lecture, let me say the following thing: an plus, so an k sits inside an plus 1 k as it sits inside as a subset which is given by the 0 set of y. So the 0 set of y is it is a hypersurface defined by y, which means you are looking at all the points where the y coordinate vanishes, and all the points where y coordinate vanishes will give you the copy of it will give you this an, okay. And the fact is that so this is the identification, okay. So an is identified with z set of y, the 0 set of y in an plus 1, okay. And mind you, this means that you are thinking of an as an is a hypersurface in an plus 1, and in this case we call it a hyperplane if you want, okay. It's a hypersurface in an plus 1 because it is a 0 set of a single polynomial, okay, where the set of points where the y coordinate vanishes is precisely a copy of an, right. And well, what is happening is that you also have a projection. This is, you have a projection map from an plus 1 into an, and the projection map is the map that takes the n plus 1 coordinates and forgets the last coordinate, okay. And the statement is that you take this projection map and restrict it to this closed subset, then that gives an isomorphism with this open subset, okay. So projection restricted to z of gy minus 1 from z of gy minus 1 to dg is a homeomorphism, and you know we will see this later, and in fact an isomorphism of varieties. This is something that we will see later, because I have to define what isomorphism of varieties is. But then if you believe this, then it's, and also believe the fact that an isomorphism of varieties has to correspond to an isomorphism of their coordinate rings, namely rings of functions, okay, then it will tell you that the rings of functions on this and the rings of functions, the ring of functions on this and the ring of functions on this have to be the same. So that will tell you the ring of functions on this has to be isomorphic to this, but that is also isomorphic to this because of commutative algebra. So it will tell you that the ring of functions on dg is this. It's correct to define the ring of functions on dg to be this. So a nice to see that in a very simple case, what you can do is that you can simply take you can just look at the plane A2, and then you can look at the rectangular hyperbola which is given by the 0 set of xy minus 1. This is the x axis, this is the y axis, okay. This x axis actually corresponds to an A1 which is sitting inside A2 given by the equation y equal to 0, okay. And if you take the projection onto the first coordinate, that is you forget the last coordinate, okay, then what you will get is you will get under the projection the image of this rectangular hyperbola will be the complement of the origin in A1, and that is precisely the affine open set dx, the complement of the point where x equal to 0. So projection restricted to z of xy minus 1 from z of xy minus 1 to dx, which is a1 minus the origin, is an isomorphism. So this is a very simple diagram that you can always remember, that tells you what's happening more generally. So I have taken n equal to 1, and there is a1 sitting as the x axis inside a2, okay, and a1 is sitting as y equal to 0, just like this an is sitting as y equal to 0 in an plus 1, and then you have this projection from an plus 1 to an, which is in this case projection from a2 to a1, and this projection is simply given by forgetting the last coordinate, which is y. That means projection onto the x axis, okay, and under this projection the 0 set of xy minus the 0 set of gy minus 1 goes to dg. For me now g is x, so 0 set of xy minus 1, which is the rectangular hyperbola, it projects onto the complement of the origin, because that is the only point that will be left out, okay, and the complement of the origin is of course dx. It is a set of all points where x does not vanish, and that is the complement of the origin, and you get a isomorphism like this, okay. And the fact that this is an isomorphism of varieties is a geometric fact, and what does the corresponding what is the translation of this fact into commutative algebra? It is just the statement that if you take the affine coordinate ring of z of xy minus 1, which is k xy by xy minus 1, that is isomorphic to k x localized at x, okay, which is defined to be the affine coordinate ring of the ring of functions on dx, okay. So that tells you I mean that gives you a picture in the simplest possible case okay, as to what is happening, and what is happening here, the same thing is happening here, right. Fine. Now so I have given you, I have given you 2 lines of justification or 2 lines to convince you that this definition is correct, okay. So let me recall them. One is that the functions on the open set, basic open set dg have to allow in evaluation of negative powers of g, okay, which is sensible enough because g does not vanish, and when a function does not vanish, its reciprocal is also valid as a function, should be valid as a function, okay. So it's natural that you should be able to invert g, and if you invert g you are actually localizing at g, and this is the ring of functions localized at g. So that is one justification. The other justification is d of g is also an affine variety, it is isomorphic to an affine variety for which the ring of functions is this, which is also isomorphic to this from the sense of commutative algebra. So this is another justification. Now I will give you yet another justification, and this is the justification essentially that it goes on that goes along the lines of the fact that you must have an isomorphism of affine varieties as equivalent to an isomorphism of their affine coordinate rings, okay. And so let me recall something from the previous lecture, okay. So you see we did the following thing. What we did was we put on one side, we put affine varieties, okay, and on the other side we put affine coordinate rings, which are just coordinate rings of functions of affine varieties, okay. I mean they are always called as coordinate rings because they essentially are based on the variables which are thought of as coordinates, giving coordinates on the ambient affine space, and the word affine is used because they are all affine varieties, okay, they are all considered inside affine space, right. And so what is the definition here? The definition here is my original definition on this side was an irreducible closed subset of affine space. So if I started with affine space A and K, well I would end up with the affine coordinate ring A. So this direction the association is given by A of, okay. So A of An is just the polynomial ring in n variables, okay. And if you give me a irreducible closed subset Z of I or Z of P, for P a prime ideal in the polynomial ring, if you take the 0 set of P, okay, that will give me an irreducible closed subset of An, okay. So this is irreducible closed, and we called such an irreducible closed subset as an affine variety, a closed irreducible closed subset of some An, and for it the corresponding affine coordinate ring or ring of functions was defined to be A of Z of P is equal to the coordinate ring, the ring of functions on the ambient affine space, the larger affine space, divided by the ideal of that variety, which is just P, okay, where of course P is ideal of Z of P. Okay, this is how we define. Now you see, and in fact I also told you that this fact that this is an irreducible closed subvariety is reflected by showing that from here to here you have a quotient, because this is just quotient by the prime ideal P, okay. And I was trying to tell you that you have a more general picture, that is on this side whatever you have, there is a reflection of that here. This is a geometric picture, this is a commutative algebraic picture, and I told you that the equivalence comes because of an arrow that is going in this direction, and I told you that arrow is actually max spec, it is given by max spec. Okay. So what I told you was, well, you give me a general affine coordinate ring. So what is the definition of a general affine coordinate ring? A general affine coordinate ring is defined to be something like this. It is a finitely generated K algebra which is a integral domain, namely it is a polynomial ring in n variables, in any number of variables, not necessarily in any number of, but finite number of variables, divided by a prime ideal. Why do I want divided by a prime ideal? Because I want an integral domain. And why finitely many variables? Because I want a finitely generated K algebra. So on this side, the more general definition of affine coordinate ring will be finitely generated K algebras which are integral domains. Okay. So so let me write that here. If you take a finitely generated K algebra there isn't enough space here, so let me write it in the next line. Finitely generated K algebra that are integral domains. Okay, this is what you should put on this side in general, and what will that be? That will be some K of, well, y1 etc ym modulo some well some p which is a prime ideal. Okay, and what does this come from? This comes from an affine variety. That is something that you can very easily see. What is that affine variety? You take max spec of K y1 etc ym. This is nothing but am. Okay, this is what we saw in the last lecture. I told you that this is a, what I proved was this is a isomorphism as topological spaces. Okay, but and I told you that that's only half the story. In fact, it is an isomorphism of even varieties, but that's something that I'll keep telling you, but that's something that I'll justify later because I have not defined what isomorphism is on this side. Okay, but just take it for that. So if you believe that, then this is an isomorphism of varieties. Okay, but mind you, at the set theoretic level this statement is just the Nullstellensatz Satz, that corresponding to a point with coordinates lambda I, you are associating the maximal ideal given by xi minus lambda I, generated by xi minus lambda I, and that is the Nullstellensatz Satz, that every maximal ideal is of this form. Okay, and let me recall that max spec was supposed to be the maximal ideals in this ring, and which is a subset of the full spectrum called the prime spectrum, which consists of the prime ideals, and that spectrum itself has had a zariski topology, and therefore the maximal spectrum, which is a subspace of that subset of that topological space, got an induced topology, and with respect to that induced topology this identification became not just a bijective map, but it became actually a homeomorphism of topological spaces, and the strongest statement is that this is in fact an isomorphism of varieties. Okay, now in this what you do is you look at max spec of this quotient K of y1 ym mod p, then this sits inside as a closed subset here, and that closed subset actually corresponds to that is the identification of z of p, which is identified with this diagram commutes. Okay, so the very identification that associates to every point of am the maximal ideal in the polynomial ring, corresponding maximal ideal, a unique maximal ideal in the polynomial ring in m variables, will associate to every maximal ideal here, I mean to every point here, a maximal ideal of the polynomial ring which contains the ideal p, because the maximal ideals in the quotient are precisely the maximal ideals in the parent ring which contain the kernel. Okay, there is a correspondence. So this is what is happening in this case. Okay, this is what we saw in the last lecture. Now what I am going to do is I am going to slightly modify, see just like I am modifying the objects on this side, I am not saying that they are affine coordinate rings. When I say they are affine coordinate rings, it means that I am already starting with something here and taking its affine coordinate ring. But instead of that, if I want to independently define it on this side, I simply define it like this: finitely generated K algebras that are integral domains. Okay, so in particular what happens is that these guys, something like this does come from here. Okay, but of course the way I defined it, it's a completely, the definition is completely commutative algebraic, it has got no geometry in it. Okay, I'm not making any reference to this side. I'm not saying that these are affine coordinate, they are the rings of functions of some affine varieties, but they turn out to be. Okay, similarly on this side what I'm going to do is I'm going to